The model in this tutorial consists of a cavern, to be excavated that is situated between two faults, beneath a large hill. Before us is the hilltop data file. Let's zoom in using the mouse wheel, while holding the Control key, to enlarge the text and make it easier to read. In this tutorial we will demonstrate how easy it is to create a deformable, or zoned, model using geometry and some new commands available in 3DEC 7. Geometry can be imported into 3DEC as either DXF, STL, or ITASCA geometry formatted files. Such geometry can be used to generate blocks and zones or for plotting as a reference image or contouring of results. The model geometry was first created using CAD software, in this case, Rhino 3D. Here we see a hilly topology and two major, intersecting faults with a cavern situated between them. Note that this object is a single, closed volume, watertight entity. This was achieved by selecting all the distinct components, for example, the faults, cavern, surface topology, and bounding walls, and using the non-manifold merge command in Rhino 3D. To see how blocks and zones can be generated from geometry, we will run this 3DEC data file step by step, while looking at the resulting model. First, let's clear any previous model information using the Model New command. Then set the model large strain on. In large strain mode, grid point positions are frequently updated to reflect large deformations. Large strain models also perform contact detection calculations, such that contacts may be created, or destroyed, as elements move relative to each other. In small strain mode, grid point positions don't change, although displacements are still updated. To run the entire data file, we can execute it using this green icon or the keyboard Ctrl-E shortcut. In this case, we will begin by just executing the first two lines. To do this, highlight them with the mouse, and click the Execute Selected Commands icon. As can be seen in the console, the model information has been cleared. Next, let's import the geometry from our Rhino 3D model. To see the geometry data, switch to the plot pane and add a geometry plot item as shown. Rotate the geometry by moving the mouse while holding down the right mouse button. There are also view shift controls, available in the right-hand side panel. By clicking the geometry plot item transparency toggle, the interior of the geometry can be seen. Returning to the data file pane, let's add a semicolon before the block generate command keyword, merge. In a data file, anything following a semicolon will be ignored. This is useful for adding comments to your data file or for modifying or excluding commands without having to delete them. Also, if you place the mouse cursor within a command, or fish function, in a data file or the command line, and press the F1 key, the help documentation will open at the relevant command or function. In this way you can see and learn about the possible keywords and background information. You may open this documentation in your browser by right-clicking on this pane. Or hide it, using the top right icon with a question mark. The keyword, maximum edge, specifies the tetrahedra maximum edge length target. The keyword, gradation volume, is the rate neighboring tetrahedra increase in size away from surfaces. Now, let's generate the model blocks from geometry by executing line 9. To see the blocks, switch to the plot pane and add a block plot item as shown. You can see that a 3-deck model, consisting of many tetrahedral blocks within the geometry volume, has been generated. If we make this plot item transparent and rotate it, we get a sense of the interior block structure. Note that you can get information about any block in the model by using the detailed information icon, an arrow with a question mark, along the top of the plot pane. Click this and then select any block to see more information about it, such as any groups it's associated with, its centroid, and ID number. Since no properties have yet been assigned, or the model solved, most of the other information is a default value. Now, let's try this again, but with the merge keyword active. Return to the datafile pane, delete the semicolon, and execute the first 9 lines again. Rerunning these commands will overwrite the current model state, so a warning message appears. Click the discard button to proceed. Now, if you return to the plot pane, you will see that the previous block plot item now shows the blocks merged together into 5 deformable, that is, zoned, blocks, based on the previous rigid blocks and the original geometry volumes. The interior structure can be viewed by making this plot item transparent. You can also hide a block group by right-clicking on it and selecting the Hide Group option. To show the hidden block, expand the block ID plot item, then expand its range, and right-click on the group item shown. Select the Delete option to remove it and display the hidden block. In addition to generating the blocks, 3-deck also assigns joints automatically, based on the original geometry. To view these, add a joint plane plot item. You can also add another plot item, as shown, to view the contacts generated along the joints, between blocks. The attributes of the plot item, such as color, size, and shape, may be changed. Available attributes may change for different plot items. Note that the plot view may be reset to the default scale and orientation by clicking the Reset View button in the View Shift panel, or using the Ctrl-R keyboard shortcut. This is a good point in the tutorial to save the model state. Saved model states can be restored to view model results or to continue modifying by issuing additional commands. The save state is now displayed in the Saved States panel along the left-hand side of the user interface. We can save the project now too. The project files tracks all input and output files, which model state as current, settings, layout, the working directory, and any plots created. Note that any associated files are not embedded in the project file. Next, we will define the material behavior by assigning a constitutive model using the block zone C model assign command, which will be more Coulomb for this example. The block zone property command is used to specify the properties required for this material. Some properties, such as dilation, have default values and do not need to be specified unless a different value is needed. Different constitutive models may require additional properties. Joint contact models also need to be assigned a joint constitutive model and properties. These are different than those used for zones. In this example, a Mohr Coulomb joint constitutive model will be used. In order to assign different joint properties to the joints defining the cavern and the two faults, a group call, cavern, will be defined, based on its extent. Fault properties will be applied to joints outside of the cavern. And properties, based on the rock, will be applied to the cavern walls. Since the model is large strain, and blocks may move, it is necessary to pre-define a set of default joint properties, in the event that new contacts are generated. At this time, we will also activate gravity. 3-Deck 7 has a new in-situ topography command to automatically initialize zone stresses based on the model's surface topology and material densities. It is also possible to specify any K ratios for horizontal stresses, with respect to the vertical lithologic stress. Next, let's add some boundary conditions. These can be thought of as representing the Earth surrounding the model. Without these, and gravity active, the blocks would simply fall, accelerating forever. To define the boundaries, we will apply zero velocities along the extent of the block grid points in the x, y, and z directions. Boundaries like these, with only one direction fixed, perpendicular to the boundary, are known as roller boundaries. Note that no boundary conditions were applied to the top of the model and these grid points remain free to move. This is known as a free surface. Boundary conditions may be plotted adding a boundary condition plot item, as shown. The boundary component, and other attributes, may be changed. Before we solve the model, we will first activate nodal mixed discretization. This is used to provide more accurate plasticity calculations for tetrahedral meshes. At this point, we will save the model state and call it init for the initial, or pre-solve, state. Running the model elastically first is good practice to initialize the model. This is intended to prevent any numerical forces leading to artificial material plastic yielding. The elastic keyword in the model save command will automatically adjust any assigned plastic material properties to behave elastically. After the model has solved, the assigned plastic properties are reinstated. Having solved the model elastically, we will save the model state, calling it hilltop elas. Now that the model's in elastic equilibrium, let's solve it with the plastic properties. At this stage, we will reset, or initialize, any block displacements and velocities. This zeroes any numerical contributions, due to initializing the model, and makes it clearer what displacements are associated with the cavern excavation. At this time, we will also add some histories, which are akin to instrumentation, in the roof and floor of the cavern to be excavated. Now, Save the model state as hilltop init. If we now continue on and simply deleted the zones defining the cavern space, it could be a significant shock to the model, leading to possible numerical instability or artificial plastic yielding, and incorrect results. To avoid this, we can utilize a zonking, or relaxation, approach. This gradually reduces the zone stiffness, while zeroing stresses within the cavern zones, over several stages. Another approach could be to excavate sections of the cavern in stages, similar to the actual construction sequence. Let's define two fish variables, named init K and init S, for the initial bulk and shear stiffness, respectively. The square brackets declare an inline fish function. The following commands are simply a repetition of two commands, applied to the cavern zone group, that reduce the initial zone stiffness, by some factor, and initializes the stresses to 0. The model is solved, and the process repeats with a smaller reduction factor, until cavern zone stiffness is very low. Let's execute all of the commands related to zonking, and save the model state, named as zonked. At this point, we can confidently delete the cavern zones and perform a final solve to bring the model into an excavated equilibrium state. Finally, we save the model at this state, naming it excavated. Let's look at the model displacements and plot the displacement histories of the cavern roof and floor. Hide the boundary conditions. Then, with the block ID, plot item selected, click the color by attribute, changing it from label to contour. Now change the value from stress to displacement. Let's invert the contour colors, so that reds represent higher values, and blues, lower ones. Using the keyboard shortcut, Shift-Y, the plot view can be shifted to look south, or down the Y-axis. To see the model interior, use the cutting tool associated with the block plot item. Adjust the cut plane attributes, to display objects in front of it. Click the block plot item to hide the cutting tool. Notice that the plot item name has changed to reflect what it's displaying. Using the mouse wheel, zoom the view towards the excavated cavern. To see the positions of the displacement histories, add a history location plot item. Now, activate the block plot item cutting plane, and use the red handle to position the cut plane to the center of the history's positions. Finally, let's add a chart, so we can see the displacements recorded during the cavern excavation. The chart can be resized using the black control boxes along its border. With the mouse cursor over the model plot, reposition the model, by holding the right mouse button, plus the left mouse button, and dragging the mouse. With the history plot item selected, click on the plus icon to add the displacement history series, 1 and 2. This concludes this tutorial.